Hello everyone, this is the walkthrough video for Summative Assignment Check-in number 4. In this check-in, we're going to be running one-way ANOVAs. An ANOVA is a statistical test that you run to compare means between 3 or more groups, or in other words, more than 2 groups. Last check-in, we ran t-tests, and you run a t-test when you're comparing means between 2 groups. But if there's more than 2 groups, that's when you use an ANOVA. Now, in the chapter that covered ANOVAs, we learned about a number of different kinds of ANOVAs. But for this check-in, we can keep it simple. We're only using one-way ANOVAs. I have some instructions up here that mention 1- and 2-way ANOVAs. You can ignore that. We're just going to run one-way ANOVAs here. If you feel very passionately and want to run a 2-way ANOVA, I mean, you can, but it's not a requirement. One thing I also want to call out, and by the time you're seeing this video, this might have changed, but just in case it hasn't, I want to make sure everyone's aware. I have some instructions here that say to refer to the cross tabulations you created in assignment number 2. For this check-in, you don't necessarily need to use the same groups that you used in assignment number 2. If you have hypotheses you want to test that are good candidates for data to have an ANOVA run, then you're welcome to use those. But if you're looking back at the crosstabs you created in Check-in 2 and you're thinking either I am not really interested in further examining those variables, or if you're thinking, I don't know if I necessarily picked variables that are suited for an ANOVA, then you can use different variables. Similar to the t-tests, if you don't end up in your final paper using variables that it makes sense to run an ANOVA on, then you don't need to do an ANOVA necessarily in your paper. What we want to make sure you're learning is when to use what type of statistical test. So you want to run tests that fit your data, not fit your data to the tests. At least not in your final paper. For this paper, to some degree, you do need to find data to fit the tests so that you can run them. But that is a one-off situation. Okay, so let's go to the template because that is going to tell you what you actually have to do. So in this template here, we see 4 rows, and in each row, we're asking you to run an ANOVA between 2 variables. In an ANOVA, you're generally going to have a categorical independent variable and a quantitative dependent variable. Of the ANOVAs. And if you are in a section with a professor who told you otherwise, of course, feel free to listen to them. But if you are not given specific instructions either way, then I strongly recommend using hospital days per decedent as your dependent variable. So we're basically just going to run ANOVAs with different independent variables against the hospital days per decedent variable. So as I mentioned, oops, spoiler alert. So as I mentioned, we run an ANOVA when we are comparing 3 or more groups of an independent variable on a dependent variable. And I also mentioned that for ANOVAs, we tend to have a categorical independent variable. So what that means is, if you know you need to run an ANOVA for this assignment, you should be looking for variables that are categorical and have more than 2 groups. So for instance, where's an example? I want to find an example of one that you shouldn't use. Here we go. Okay, so in my version of this data set, in column Z, I have this % enrolled in hospice binned variable. And that one, I'm going to filter it for a second so you can see. There are two categories, 50% or more and less than 50%. Now, this is technically a categorical variable in a sense, because it's not giving you specific numbers, it's just giving you categories, aka less than 50 or 50% or more. But this is not a variable you would use for an ANOVA because there's only two groups. You want to make sure you choose an independent variable that has more than two groups. For my example, I'm going to use region, which, oh wait, that's not region. I'm going to use region. Here's region, I found it. And as I'm going to use that as my independent variable. And then as per usual, I'm going to use hospital days per decedent as my dependent variable. So I'm going to copy those two columns into a new tab just to make everything cleaner and easier and just to avoid any confusion. Okay, now I'm going to make it bigger so you guys can see. So first step is I'm going to take stock of what the different categories of my independent variable are. In this case, it's region. A couple ways you can do this. You can either make a pivot table by highlighting the column, clicking insert, clicking pivot table, click OK, and then just put region into rows. If you do this method, you're not going to need to show the pivot table anywhere. Show you all the different categories there are: Midwest, Northeast, Southeast, and West, in my version anyway. Or you can filter it. So I'm clicking on the 1 to highlight the first row. Then I'm going to sort and filter. Then I'm clicking filter. And then when you click the down arrow, it shows you all the different categories. Now, if my memory is correct, I think most of the categorical variables that you would realistically perform an ANOVA on aren't going to have a crazy amount of groups. If there is a variable that is categorical, but it's basically different for every single hospital, for instance, city, I wouldn't recommend using that because there's just way too many groups to keep track of and you're not going to find any meaningful patterns. So I recommend one where there's enough groups where if you're looking at it, for example, if you're seeing small, medium, and large, you could pretty easily describe each of the groups, right? If there's literally a different city for every hospital, you're just not going to find any patterns there. Okay, but so now I see what my groups are. So now in a couple of columns over, I'm going to write each of these categories in the columns going across. So we got Midwest, Midwest, Northeast, Southeast, and West. Okay, now we're going to, and I'm going to unfilter it. Now we're going to use a very similar process to what we did for the t-tests, where we're going to paste the relevant hospital days per decedent under the appropriate region. So actually I'm going to filter it again, and I'm going to sort by region just to make sure the regions are all together. And now in this particular data set, or at least in my version, the regions were kind of already all together, but I think for a lot of the categorical variables in this data set, they are sort of all mixed in. So you definitely want to make sure you sort before doing this, just to avoid a headache later. So starting with Midwest, I'm going to copy all the hospital days per decedent that are next to Midwest, and there aren't that many. Or the Midwest column. Then I'm going to do the same for Northeast. Then I'm going to do the same for Southeast. I'm going to do the same for west. Then I'm going to open my analysis toolpack and go into ANOVA single factor. For the input range, I'm going to want to select all the data starting from the column headings for the different categories. So in this case, Midwest through West. And I want to go down to whatever the lowest data point is. So, or I guess rather, whichever column has the largest number of data points in it, you want to go to the end of that column. So in this case, I'm going down to 104. So what that would come up as is, D1:G104 for where I put my particular columns. And again, if it doesn't automatically populate when you highlight it, you could write that out as well. So just make sure, so actually I want to point this out. So you'll notice the column that has the most data points in my data set after, putting the hospital days per student into the appropriate columns is column F. But I'm still including the blank cells from the columns that don't go so far down in this range. So it goes to G104, even though the last data point technically is an F104. You basically want to make sure that all the data is contained in this rectangle. So that does mean you're going to have some blank cells, and that is okay. Okay, now for the output range, I'm just going to pick a random one that's empty and click OK. And let's take a look at our output. So what we have here, in this first table, we have our descriptives. I'm just going to say off the bat, you can pretty much ignore some. That's not used for much of what we do in statistics and data analysis. But we have a count for each group. So we can see there are, in my data set, I have 24 hospitals in the Midwest, 48 in the Northeast, 103 in the Southeast, 76 in the West. I can also see the average for each group. So 8.7 in the Midwest, 10.1 in the Northeast, so on and so forth. We also have the variance. Going down below, we have the actual ANOVA table. I think the value in this table you're probably going to be the most interested in is the p-value. Recap from last time, this is going to happen a lot because we have such a big data set. If you see E minus something in your p-value, that means it is a very, very, very small decimal and it is less than 0.05, which generally 0.05 is, the value of interest that if it's below that, we're going to say it's significant. So this would mean that it is significant. So if I were actually doing this assignment, I would go back to my template and I would say analysis of ANOVA test between variables blank and blank. I would say I should make it enable editing. I would say the variables are, in my case, region and and hospital days per decedent. And then I would say, and I just want to say, you can probably tell right here, sometimes the template gets a little wonky and the rows and columns get smaller. You can just resize them by clicking on the little lines in between and dragging them if some of the text isn't showing up. And then I'd say the ANOVA results showed there to be a significant difference among regions in hospital days precedent. And I'm sorry for making so many typos. I swear public typing is worse than public speaking. Now let's break down that sentence a little bit. So, in my ANOVA here, we are looking at these different columns, which each represent a region, and the numbers in the columns represent the hospital days, or the average hospital days per decedent for different hospitals. So this is saying one hospital in the Midwest has an average of 9.3, another hospital in the Midwest has an average of 8.6, another 9.4, whereas this hospital in the Northeast has an average of 11.4. This one has, an average of 14.1. Here we have two hospitals in the Southeast with averages of 10.3, and so on. So what we're saying is, when we come up with the grand average for each column or each region, the average hospital days per decedent for each region, we are saying that there is a significant difference among regions. In other words, the difference in average hospital days per decedent among regions is greater than the difference we would expect to see if these results were just due to random chance and there was no true systematic relationship. Now, what this doesn't necessarily tell you is exactly which groups are significantly different. So we know that from these results, we can say that these averages aren't all the same, but we don't necessarily know that each average is different from each other average. For example, we have two regions where their averages are kind of in the 10 range. It's possible that maybe West and Northeast are not significantly different, but Midwest and Northeast might be. And just to be clear, that is just an example. I'm not saying they are or aren't. I'm just giving an example to speculate. If you want to take this a step further, you can refer back to your textbook and look up Fisher's least square difference, I think, test for equality of variances. Basically, you want to go back to the Fisher's test in the ANOVAs chapter, and that will show you how to compare each group average and figure out exactly which groups are different from one another. You don't have to do that. That is totally optional. That's only if you want to take it a step further. But what you do need to know is, when you see that there is a statistically significant difference in an ANOVA, if you don't run some additional test, you don't necessarily know which groups in here are different from each other until you run that test. For the purpose of this assignment, it's sufficient just to say whether there is a significant difference somewhere. You don't need to find out which two groups are different, but if it's something you would like to examine further, or if it's something you really want to elaborate on when you're doing your paper, you're welcome to, but it's not required. Yeah, and so you'll do the same thing with some other independent variables, and basically just say what the variables are, and then give a brief summary of the outcome. And that is check-in 4.